Yeah, so good afternoon. My name is Guido Dalessi. I'm from the company Elestor, which stands for electricity storage. You might think what a battery is doing in this audience, but I'm pretty sure this will be clear during my presentation. This should work. Yeah. Maybe just a step back to look at the energy transition, which is a common item in the presentations today. In the Netherlands, this is just a very small part of the world. We see that our grid is stuck. There's big traffic jams. It's hardly possible to feed in any electricity. And with more sun and wind, it will only become worse. Another example you see here in the UK. This is a graph of the curtailed energy. So that's when there is a total overproduction, wind parks and sun parks are stopped, are taken out of operation. And here in this graph you see how much energy was not generated, that could have been generated if the grid could handle this. So this is really becoming an exponential growing problem now. Obviously, one of the ways to mitigate these traffic jams in the grid is to store electricity. And this is what my company Elestor is doing. So we have introduced a new type of battery based on flow battery technology. Maybe not common to you, but I'll go into this a little bit. And that is for large to very large scale storage of electricity. The larger the better, because the larger the more economic the solution becomes. I already mentioned it's based on flow battery technology. If you are familiar with that, then you know that there are many types of flow batteries, all working according to the same fundamental principle, but using different chemicals. The chemicals that we have chosen are hydrogen and bromine. And the reason for that, I get back to you. Essential for a storage technology on this scale is that you can reach very low storage cost per megawatt hour. Electricity is stored when it has a low price, when there is an overcapacity, and you want to feed into the grid maybe the next day when the price is high again. And this is where you make your margin. This is how you make your return with a battery. But the storage itself also costs something, And the lower that amount is, the lower the costs per megawatt hour, the better your business case behind storage is. So this is a formula. It's a simplified form about levelized cost of storage that gives you let's say, the main factors determining what it costs to store 1 megawatt hour of energy. And of course, this has to do with what the system costs, but also how long the system lives, how many times you can charge and discharge it, and the efficiency. So there's a bunch of factors that determine in total really what it costs to stay overnight in this battery. So yeah, I mentioned we are using hydrogen and bromine, especially bromine is, I think, not such a common known chemical element. This table gives you a bit of the global reserves, and then you see that bromine is really there at astronomical quantities. And again, in my previous slide, I talked about levelized cost of storage. If you want these to be low, you better start with very low cost chemicals. So this is one of the reasons that we have chosen for bromine. It's a chemical element similar to chlorine. It's very reactive. That means that we have to take precautions to work with it, but it's also a blessing because it enables you to charge and discharge the battery really fast. Bromine is found in the sea. Unlike lithium and vanadium, it's not restricted to certain countries, actually dominating the supply. I once gave this presentation in the EU, in Brussels, and I gave it the title, Are we going from OPEC to LEPEC? If you understand what I mean. Because this dependency on a very limited number of suppliers and a high demand is a typical situation for oligopoly. That cannot happen with the bromine. It's from seawater, so it's cheap today, and it will be cheap always. This is a picture. I will go through it fast, giving a bit of an idea of how electricity prices volatility will change in the near future. You see, 2022, we are just at the start, and in this volatility, obviously there is the business case for storage. There will be more days with high electricity prices, and there will be more days with negative electricity prices. That's good for battery storage. A bit about technology. So here you see, and now we are, I think, connecting a bit a picture with the fundamental working principle of the flow battery. You see two big tanks, and these tanks you need to store the hydrogen and the bromine. And each tank forms a closed circuit. So what is in this tank is circulated, is pumped around. The left tank and the right tank each have this closed circuit. And these circuits meet each other at a membrane. That's a special layer that allows certain ions, usually protons, to pass through. So when you charge and discharge, basically the chemical composition of what's in both tanks changes. So this is the general picture. This is the solution that Elestor has developed. So I hope you recognize again the two tanks and the membrane in the center. The left tank contains hydrogen bromine, HBr, that's a solution. And the right tank is to store hydrogen. So how does this work? Very quickly and simple. If the battery is completely discharged, the right tank is empty. There's no hydrogen. Only the left tank contains hydrogen bromine. And when you apply a voltage, when you start charging the battery, you split basically the HBr into an H plus and a Br minus. This H plus can cross the membrane and forms hydrogen gas at the right side. So if that was all too fast for you, just remember that this battery produces hydrogen while charging. It's collected in the right tank, and you need that electricity again for that hydrogen, again for discharging. So in total, it's a closed system. You don't need to add hydrogen or bromine. It's not consuming, it's using these chemicals. The essential difference of flow batteries and, let's say, conventional batteries is that the power expressed in megawatts and the energy expressed in megawatt hours is decoupled. So you can build any combination. And the power is determined by the surface area of the membrane in the center. The energy of the battery is determined by the size of the tank. So that means that you are completely free in configuring these kind of systems, and especially for long duration, let's say from 8 hours and more. So you need bigger tanks to bridge longer periods of time. This technology becomes much more economic than, for instance, the lithium-ion batteries that we know. If you would look for a storage solution for a couple of hours, lithium is definitely the better choice. If you go from 8 hours and more, flow batteries become the better choice. And that's of course because what's in these tanks, I just told you, is extremely cheap. So our energy part is very low cost. In practice, this is not a single cell. There are a number of cells stacked on top of each other, connected in series, and that forms a building block of a certain power. And then, for instance, in this example, that's a 10 kilowatt block. So if you want a 100 kilowatt battery, you connect these in series, these modules, to get the 100 kilowatt. Yeah, this is how such a system looks like. In the yellow container, you have these power blocks. And in this case, you see this dome, and this is one of the options to store hydrogen. You can do that in a dome. That's, of course, at atmospheric pressure, and that means this is only viable for smaller batteries. No, we are not talking about hundreds of megawatt hours here, of course. If you want to do that, we can store the hydrogen in pressurized tanks. Yeah. So there are many options to do this. Obviously, to store under atmospheric pressure is energetically the most attractive option because compression also costs energy. Yeah, then this flow battery, since we are using hydrogen, has some unique possibility to connect to hydrogen infrastructures and to electrolyzers. I skipped this one. Well, you see here, going back to the basis, you recognize the two tanks and the membrane stacks in the center connected to the grid. And then imagine that you remove this hydrogen tank. It's can be a big part of your system, also quite an expensive part of your system. And yeah, then you end up with almost half a battery consisting of one tank containing a liquid, the hydrogen bromine, and the membrane stacks. And now imagine that you have a hydrogen infrastructure available, or a big tank, or a pipeline, or whatever. Then we can use this pipeline as the storage for the hydrogen, because the battery produces hydrogen while charging, puts that into the pipeline, and takes that again from the pipeline while discharging. So there is net no consumption from the pipeline. But it prevents that you need a big storage tank. It reduces the cost, it reduces the footprint, obviously, and it lowers the levelized cost of storage further. And that was the aim that we have in our company, to reduce that to the absolute minimum. Yeah, you can take that a bit further. Oh, I didn't show that. You can also integrate it into electrolyzers. We did a study together with an Austrian energy company called Verbund to integrate it in their electrolyzer setup. And by using this kind of battery connected to a hydrogen grid, we can reduce the production cost for hydrogen with 20 to 30%. And that will be installed next year. A few slides about Elestor. Today it's a team of 26 people. The company was founded in 2014. We are really well connected to the scientific world, Fraunhofer Institute. We have a few people doing their promotion at the University of Eindhoven. So 26 people, we are at the verge of expanding very fast. What is probably most appealing to you is the contract that we signed about a year ago with Vopak. I mentioned flow batteries need large tanks, and obviously, sorry, Vopak has a lot of knowledge of how to store liquids and gases on a really large scale. So we've been talking actually for a couple of years, because before we reached that point and started this cooperation, today we are part of their new energy strategy. So they didn't just buy a battery and exploit it. It's a longer-term future picture that Vopak sees to integrate this kind of technologies on their seaport terminals. Initially, this will be a 3 megawatt hour system, and that is to validate the business case analysis that we did a couple of years ago. But eventually, this will grow to hundreds of megawatt hours, which fits with the tank sizes that Vopak uses on their seaport terminals. Yeah, in addition, just to give you a bit of an insight, yeah, I mentioned this technology is for large and very large. We recently signed a contract with a company which is probably the largest wind park developer in the world. There are more projects in the pipeline, and maybe a nice one to mention is the, thank you, is the Sun Cable project. It's a very ambitious project in Australia, northwest Australia. There's a huge capacity of PV, so solar, that will be built. Cable will go to Singapore and Indonesia from there, and obviously they need really a big storage capacity, a huge storage capacity, I would even say. So my company is now on the short list of preferred suppliers to deploy 1 gigawatt hour until 2030. Yeah, I just mentioned the company is at the verge of really a big growth. We are with the pen on the paper to sign a very large funding round. That's in the order of 10 millions of euros. And that is really to build up the production capacity. So far we have been building the systems ourselves, which is of course far too expensive, far too slow. The world is there. There is an increasing demand, especially long-term, long-duration energy storage is becoming more and more in the picture. And so the company will grow, and this is a bit of a picture of how this production capacity will be built in the next 4 to 5 years. That's what I wanted to share with you. I hope it was interesting and appealing. If you have any questions, we can do it probably still now, but otherwise I will be around here in the next 2 hours. Thank you.